Well, hello everyone, and welcome back to the Tin Barn. I'm Pragmatic Lee, of course, and today's video is going to be a little bit of a follow-up to the last series I posted. In the last series, I made this speed handle for my mill vise, and there were several comments about how the hex was milled out. Of a lot of interest in how that was laid out and done. And I think I probably answered everyone's questions during that video, but it was hard to see. This was only a 14 millimeter, a little over a half inch. So in today's video, I'm going to do something, it's not going to be a project, it's just going to be a how-to, if you will, and show you how to mill out a hex out of a piece of, I'm just going to use some 1/8 inch piece of stock here, just something I can use as a scrap piece. Anyhow, we're going to lay out a hex and mill it out two different ways on the milling machine. The first one, we're going to use the DRO and a rotary table, just like I did in the video where I made the speed handle. The second one we're going to do, though, is for the benefit of those that maybe don't have a DRO or don't even have a rotary table. All we're going to use on that is a compass and a protractor. And it's not going to be a situation where we set up the compass to a distance and try stepping it around a circle and see if we come up with 6 even spaces. When we come up with our value to set the compass, it will be exact the first time. So stick around for that second part as well. I've got to get a rotary table set up on the milling machine. But before I do that, I'll move the camera around here and show you a little bit of math ahead of time of what's going to be necessary to make a couple of computations in this first milling using the DRO and the rotary table. So I'll move the camera over here. What we're going to be milling today is a hexagon that is hopefully large enough that you can see what I'm doing and follow through what I'm doing. We're going to do 1 1/4 inch across the flats. If you recall from that previous video, there was a constant that we used to determine what the long diameter was. So we know the small diameter is 1.25 across the flats. Big D, the large diameter, is the small diameter times 1.54701. That is a constant. That comes out to 1.443. And we'll need the radius later. If we divide that, we get 7.22. But across the points on our hexagon, if it's 1 1/4 across the flats, it'll be 1.443 across the long points. Now, if you don't like using constants, there is a trigonometry formula for that, which is small d, the distance across the flats, divided by the cosine of 30. There are 6 angles across here, or there's 6 flats, 2 angles at each one. Each one of these angles is 60 degrees, so half of that is 30. So small diameter divided by the cosine of 30 will give us this same number right here that the constant did. But it's the 21st century. So let's see what happens when we ask Siri. Siri, what is 1.250 divided by the cosine of 30?
Let me think about that. The answer is 1.44338.
Thank you, Siri.
Your wish is my command.
Okay, 1.443 She gave us the same number, carried out a few more decimal places. So very simple to find out what the large diameter is. Before I go over there, I want to lay out one more thing here. Piece of metal we're going to be using is a 2-inch piece of 6061. So I'm going to scribe a line down the center. Now what that serves, what that center line will serve for, is if you want the flat of your hex, say in line with the flat of your workpiece, you'll need to start on the center line here, and make your first 0 degree over here. All right. When we get to the DRO, it's going to ask us the starting angle and the ending angle. So we're going to start at 0 right here, and we're going to do 6 holes, if you will. We're using the bolt hole pattern. So 0, 60, 120, 180, 240, 300. So our ending angle is 300 degrees. So hopefully all that'll make a little bit more sense when I get over to the mill and setting up the rotary table. Several other comments on that previous video series where I was using the rotary table were questions and comments about the pallet that I have on here. This is a piece of 1/2 inch thick 6061, just aluminum stock, and I've got it drilled and tapped on a 1-inch square pattern with 1/4-20, and I've laid it out on a 1-inch grid. If I were going to do anything different, and I may sometime soon come back and go in between these with some more. When you get out around the edge here, it would be kind of nice to have a few more holes in there. But this is the pallet. This is a 6-inch rotary table. I think there's 45 holes in that, so you'll have a screw-in good time if you decide to build one. All right, I have the rotary table centered now, got the quill centered over the center of the rotary table. We're going to lay out, use the DRO now to lay out our bolt hole pattern. On the DRO, we choose the bolt hole pattern icon, and I had the DRO zeroed out. So we're on the XY axis, meaning that we're on a vertical mill. We're going to start with center. All of our work is starting off the center at 0, 0. The diameter, remember Siri told us that the diameter was 1.443. All right, number of holes is going to be 6. Starting angle is 0. Ending angle is 300. This was still set up from the last video where I made the speed handle. So, our number 1 hole, it says to move over, and I'll get this camera zoomed in a little bit more so you can see what we're doing here. All right, we want to move our DRO to 0 so that it reads 0. And we're locking down the X and the Y axis. I have a sacrificial piece underneath our workpiece here. Second hole, again, moving to our DRO reads 0. On both axes. Third hole. Fourth hole. fifth. And the final hole. Okay, over here on the DRO, we can leave the bolt hole pattern routine now. We're back in our normal mode, so let's go back to 0. All right, I'm going to get the camera repositioned a little where maybe you can see what we actually have at this point. All right, what we just did was drill a hole. I used a 7/64 drill bit, drilled just a small hole on each of these 6 points that the bolt hole pattern on the DRO gave us. Now, unlike the last video on the speed handle, I milled out everything out of the center of the DRO, center of the hex, I'm sorry. In this one, we're going to leave it. There's no need of milling all that out. Before on speed handle, I could drill out 95% of it. But I'm going to use a 3/16 end mill. The reason I'm using a 3/16 instead of a 1/8 is because I broke the 1/8. So 3/16 is as small as I got. But that's 0.188. Half of that is 0.094. Now we're cutting out the inside, so we're going to need to subtract that. Remember we said our hexagon across the flats was 1.25. That was across the flats. That's our small d, 1.25. Half of that is 0.625 minus half the diameter of the end mill, 0.094, means that we need to step over 0.531 for all sides. All right. This was setting at 0. So we're going to step over. See, here's our 6 holes. We're going to step over on the y-axis 0.531 and lock that down. Lock down the y. Now on the X, we want to move to where we just barely break into that hole. Now we're going to move until we just barely break into the hole on the other side. And I'm going to put a little bit of air on there so I can get the chips out of the way. All right, that's just barely broke into that hole. Now we'll go 0.531 on the other side of 0. And again, just where we just barely break in to the circle. We'll go down the thickness of our material. Okay, let's see how much you can see there. All right, what we just milled was this bottom down here, across this flat, and across this flat, on what we're calling the top. Now, I'm going to unlock the rotary table. Whoops. Unlock the rotary table and go 60 degrees. Now what that has done for us, I can get this, that has turned so that the next 2 sides are in line perpendicular with the y-axis. So we'll move 0.531 again, being sure on the x-axis that we're just barely going into that hole. Now to the other side on y. 531. Now on the table we could go another 60 degrees, or all I'm going to do is simply go 60 degrees in the other direction. Let me stop there and see just how much of it maybe you can see at this point of what we've got. We've got the flats on 2 sides, or flats on 4 of our 6 sides milled out. So we'll come to 300 degrees over here, go past it and come back to it. 531. And our final side, and our centerpiece may come flying out, we'll see. And there's what the centerpiece looks like. Of course, we're going to throw that away. Needs some deburring. I didn't quite get it deep enough on this side. Let me carry this over to the workbench. All right, so there's our hex. I did a little deburring and cleaning up into the holes. I just wanted to be sure when I was milling on these flats across here, I didn't go too far in there. So you wouldn't have to go too far before you'd run into the flat on the adjoining side. You can make this, the smaller the drill bit and the smaller the end mill, the less prominent your corner holes are, but for me that just adds a little character to the hexagon. What we're going to do now is lay out this same hex, but we're going to do it without the DRO or even the rotary table. Back at the beginning, when we calculated what this outside diameter was, we still needed to know that. You'd still need to do this math here. The small diameter times either the constant 1.154701 or do the trigonometry d divided by the cosine of 30. In any case, we know that the large diameter across the long points we determined to be 1.443. If we divide that by 2, the radius is 0.722. So on the calipers, I'm going to set up 0.722. And since it's kind of hard to lay that out on there, here's what I like to do when I'm drawing something on paper like this. I've got the caliper set at 0.722 now, and I'm just going to take these points right here and just find them in an arbitrary location, dig that point in a little bit, dig that point in a little bit. Now I'll use those 2 points. I'm going to draw this on the paper first. Then off camera I'll do the exact same thing over here. It'd just be easier for you to see with it done on the paper. So I'll set that in one of the holes, and I'll bring this over. There. Now, we set up on our mark over here, or on our center point that we've got laid out, and we draw us a circle. It's kind of hard to do this reaching over the camera. All right, one of the characteristics of a hexagon, very interesting characteristic, is that the length of one of the flats here, this length across here, is exactly equal to the radius of our big diameter. So with the caliper set left just like they are, again, we're not using a set of dividers where we're going to guess at it and walk around it and hopefully keep messing until we come to the same spot. We're going to set this on our center line. We're going to make a sweep right there, a sweep right here. We'll move it over, sweep, sweep, and guess what we've got? We've got our same 6 points right there that we had, that the DRO laid out for us. Now all we've got to do is take our flat edge, straight edge, and connect those 6 locations. I'll do that off camera on this piece, actually scribe that in. I'll put some Sharpie on there and scribe that in. Then when we get to the mill, we're not going to use the DRO nor the rotary table. We're going to clamp this down to the table with a piece of sacrificial material under, of course, and we're going to mill to the line. We're still going to drill our 6 holes, but then we'll mill to the line each time. All right, I have the piece over on the mill table now. I've got the rotary table off. What I'm using for a sacrificial piece right here is a piece of PVC board from the local builder supply. When I put this on there, I didn't try to spend a whole lot of time indicating it in on the x-axis. I just got it close by eye, and then I ran a mill down this edge right here to get an edge in line with the x-axis. Now, please understand that what I'm going to do right here, I don't by any means try to, not by any means trying to convince you it's going to be as accurate as using the DRO and the rotary table. But I think it'll be close. So what I've done is just like we did on the paper, drew the circle around, and then set up on the center line, arc, set up some center line, arc, and then I've punched down, used the center bunch and punched the holes. Now 2 things I know right here is when I get centered on one good hole, I've got the DRO turned off, so I won't even be tempted to look at it. If I go there, now if I go on the y-axis, well, let me drill this one. Now I know the y-axis is going to remain the same. So even if I didn't punch down exactly right, and that one tried to skate just a little bit there. Now I also know that from this hole right here, that X is going to remain the same. And really, what I should be doing is using a center drill on that and starting these. You can probably see it the way the camera is zoomed in here, that it's starting to, or it's wandering just a little bit there. But it'll be all right for what we're doing here for in theory. Now if I come back to the center line we put on there, and that should remain the same on the X as well. Now what I will do is put the end mill back in, and I've got it scribed there, but what I'm looking for more is to just break into this hole that I drilled on the x-axis this direction. As far as the y, shoot for the center of it and then mill over to this one. All right, I've got the end mill in there now. I've come over to this side right here, and on the y I'm comfortable that I'm at approximately halfway, or I'm at halfway this hole right here. We're going to stay on that same axis. I'll raise up just a little here, come over. Now we'll penetrate our piece, and we're going to move over again until we just cut into that hole good. We're just breaking into the hole. All right, I'm going to leave the x-axis set right there. Raise up, come on the Y. Right there's about halfway our circle. Now, if we were on the rotary table, we would rotate 60 degrees. We're not on the rotary table, so here's what we're going to do now. We're going to leave our sacrificial piece in there just like it is. And remember I said we're going to use the protractor? So we're going to want something right about in this area right here. And that's set on 60 degrees. Put us a mark there. And I'm going to get this clamp down, held in position here. Not sure if you can see that on the camera or not, but I've got that right on that line there. Now we're going to repeat that process. Now you can probably guess what we're going to do now is get us another 60-degree mark, complements of that one. So I'll come 60 on the other side. Okay. All right, I'm going to take that out just like the other one. I'm going to deburr it. And just like the first one I cut, I should have gone a little deeper in my sacrificial piece. I wouldn't have as much deburring to do. All right, here's our finished product. Let me put a little something behind that so you can see, maybe see a little better. There's our 2 hexes. See which one was done which way. Alright. This one was done with using the DRO and the rotary table. This one was done just manually milling to the line or milling to the holes. What you need to do is mill to the center of the hole each time. Mill to the center of the hole. Rotate 60, do the same thing, rotate 60 in the other direction, and do the same thing again. But it's really not rocket science. I know I threw a little trigonometry at you to begin with, but it's fun. I enjoyed it. And if you ever need to mill a hex, any size, just remember, you'll likely know what the flats are, the distance between the flats. So multiply that distance times 1.154701 is the constant. Or if you want to ask Siri, ask her what your small diameter is, 1.125 or 1.250 in my case, divided by the cosine of 30. Hope you enjoyed it. We'll see you in the next video.